Okay guys, let's take a look at today's lesson. We're going to learn two more theorems. There aren't a lot of theorems that we have to learn in calculus. You know, unlike geometry, I know some of your favorite theorems come from geometry. We have tons of theorems in geometry, but we really only have a handful in calculus that we have to know. And the theorems that we go over are pretty important. You've got to know them. So let's start with Rolle's theorem. Like the other theorems, we have criteria to be able to use it. And so let's look at the criteria. What has to happen for us to be able to use Rolle's theorem? First of all, we have to know that the function is continuous at every point on the closed interval. Okay, that's criteria number one. So the function is continuous every point on the closed interval. Criteria number two, it has to be differentiable at every point on the interior or the open interval. Okay, so the first criteria, continuous on the closed interval. Second criteria, differentiable on the open interval. Third criteria is actually the most restrictive criteria of all, and which is one of the reasons why we don't use Rolle's theorem a whole lot. This tells us that the y values of the endpoints have to be equal. Okay, so you can imagine that a lot of intervals are thrown out because that is not true. So this is a very restrictive theorem, but still it is used and is important. So three criteria to be able to use it. We need to be continuous on the closed, differentiable on the open, and the y values of the endpoints have to be the same. All right, if all of that is true, if those three criteria are true, then we have at least one number c. Now keep in mind they mean c is an x value. I mean, I know they like using the letter C, and that really confuses students, but they're talking about that there's at least one x value in this open interval, that this last thing would be true, that the first derivative would be equal to 0. Now, why do we care if the first derivative is equal to 0? Didn't we just talk about what's important? Right, those are critical numbers. That's where you can find maxes and mins. So that's Rolle's theorem. There's three criteria to use it, and if those criteria are true, then we are guaranteed at least one number where the first derivative is 0. So here is a diagram, a visual of what this theorem is talking about. Notice how, here's my endpoints, A and B, my y values. See, my y values are the same. This is a polynomial. It's a curved function, so it is continuous and differentiable on the interval, so it meets all three criteria. And in this particular case, we actually have three x values where the derivative is 0. Of course, they're naming them by c's because that's the variable they're using. So c1, see, it's 0 here, so the first derivative is 0. c2, first derivative 0. c3, okay, so in this case, we got three places where the first derivative is 0. We are only guaranteed one. That doesn't mean that there will only be one. We're just only guaranteed one. Okay, so that's how Rolle's theorem works. Okay, and here's a diagram of what that would look like. So let's practice it. We're asked to verify that the function satisfies the three hypotheses. Now that would be a great formula quiz question, of course, but I'm not going to use the number 3. I'm going to say, what is the hypothesis of Rolle's theorem? And you would be expected to list each of those three things. Okay? Yeah. No, just say continuous. You can say f of x is continuous on the closed interval, differentiable on the open interval. Yeah, you can say that. That's fine. It doesn't have to be, it has to give me that information. It doesn't have to have every word for word there. All right, so let's verify. So number 1. We need to check to see that the function is continuous. Now this isn't a very difficult way. We don't have to go back to definition of continuity to do this. Okay, now that's a cool definition, and you probably already know that, and you probably could like that. But really, what we want here is inspection. It's okay to look at it and determine whether it's continuous or not. You don't have to prove it. With math or words, just look at it. Okay, this is a polynomial. Right, we know polynomials are continuous. So we would say continuous on the closed, check. That's our first check. Number 2, is it going to be differentiable? Yeah, polynomials are differentiable everywhere, right? We know that because we know what a polynomial, we know the behavior of polynomials. So it will be differentiable on the open interval. Check. Our third check is to see that the y values of the endpoints are the same. So let's see, f of 0 would be 5, and f of 2, after you sub a 2 in, let's see, that is also 5. So the y values of the endpoints are the same. Perfect. We have satisfied the 3 criteria of Rolle's. So we have verified that the function satisfies the hypothesis. Now we're going to find all numbers c that satisfy it. Well, let's look over and see what it says. How are we going to find those c values? What are we going to do? We're going to take the derivative, set it equal to 0, right? Solve for x, and then now, in order to go from an x to a c, it has to be in this closed interval, or the open interval. Right? It has to be. So not all x's can become c's. I guess it's like a promotion. You know, you're going to go from an x to a c if you're in this interval. So let's do that. So let's take the derivative. So f prime of x is 3x squared minus 6x plus 2. Okay. We set that equal to 0. Yes, some of you already see this. Our little friend is not factorable. I know. We have to pull out our old favorite, old standby, quadratic formula, which we all know and love. So we pull old quadratic formula out, 6 plus or minus square root of 36 minus 4 times 3 times 2 all over 2 times 3. Now, I'm not going to take you through the arithmetic of that. We are in BC Calculus. We should be able to do that. So let's just go straight to, after you finish your arithmetic, you're going to get 3 plus or minus 3 root 3 over 3. Okay, so like I was saying, that's what x is equaling. But in order to get the promotion, we need to make sure that they're in this interval, that to become a c. All right, square root of 3 is between square root of 1 and square root of 4. So, I don't know, maybe 1.5. We can just estimate a little over 1.5 perhaps. So if I do 3 plus 1.5, that would be like around 4.5 over 3. That number is going to be, yeah, it's going to be between here. Right? It's going to be bigger than 1. It'll be between here. So that one's okay. Let's try the negative one. So if I do 3 minus like 1.5, it would be what, 1.5 over 3? That's still between 0 and 2. So both of these qualify. Okay, both of them qualify. So c is going to be 3 plus or minus square root of 3 over 3. And there is our first theorem for today. Are we okay with that? Rolle's theorem? Okay. Let's do our second and final theorem, which is mean value. Now, there aren't many things that you are going to be allowed to abbreviate on the AP exam. Mean value theorem is so important that they actually know what MVT means. You can actually abbreviate mean value theorem. There aren't many things you can abbreviate, because you can imagine students can abbreviate all kinds of things and the reader would have no idea what they're talking about. In this case, it is so well known that, yes, you can abbreviate mean value theorem. So let's talk about when we would use it, or what are the criteria to use it. So it starts out, we are letting y equals f of x be a continuous function on a closed interval. That sounds familiar, doesn't it? That's how Rolle's theorem starts out, number 1. Number 2, we want to be differentiable on the interior. That sounds exactly like Rolle's theorem, right? That's the same thing. Then it stops. Okay, so their criteria is the same, except mean value theorem does not require that the y values of the endpoints be the same. So it is much more usable. Well, let me say, we can use it more frequently than the Rolle's theorem because it's not as restrictive. So let's look and see what that gives us. Well, that's great. So if that's true, if those two things are true, then we are told that there is at least one point C, which of course they mean that's the x value. There's at least one x value in this open interval where this little guy right here is true. Okay, pretty important. Let's talk about what that means. This over here on the left side you should recognize, right? It's average rate of change. Slope of the secant. Right? The formula. And over here, so this is saying that at least one place, the slope of the secant, or average rate of change, will be equal to the instantaneous rate of change, the derivative. That's pretty big. Okay? That's what this theorem says. Now this is a picture of what that looks like. So here is our A and our B. We are continuous and differentiable. Continuous on the closed, differentiable on the open. So there is at least one place. See, here's our secant line right here. There's at least one place where the slope of the secant line will equal the slope of the derivative, the instantaneous rate of change. There will be at least one place where they're the same. And we can see from this diagram, there's one place because those lines are parallel, their slopes would be equal. Okay, so that's what this theorem tells us. Okay, that's a big deal. Questions about the theorem? Okay, so let's practice using the theorem. So the first example just asks which functions satisfy the condition. So we only have 2 conditions to work with now instead of 3. Number 1, so let's start with this one. So number 1, is this one continuous on the closed interval? Yeah. Continuous on the closed, check. Is this one differentiable on the open? Now, some of us can look at it and see. I'm going to go ahead and find the derivative so that we can actually inspect the derivative and see what's going on. You don't have to write the derivative down for me if you're doing this. If you can do it by inspection, that's fine. But let's go ahead and find the derivative. So for this one, the derivative would be 2/3 x to the negative 1/3, or rewritten 2 over 3 cubed root of x. Is there somewhere that this derivative is undefined? Yes, it's 0. Is 0 in this interval? Yes. Well, that's a deal breaker. Right? That's a deal breaker. It is not differentiable on the interval. So, mean value theorem is not going to apply in our first example. So, differentiable on the open? No. So, it does not apply. No. A is no. Okay? So, let's look at part B. And let's check that one out. So number 1, is it continuous on the closed interval? Yes. Number 2, we want to see if it's differentiable on the open interval. So that's checked. So let's find the derivative. So f prime of x would be 4/5 x to the negative 1/5, or 4 over 5 fifth root of x. Is there a place where this derivative is undefined? Yes. Is it 0? Is that a problem for us? It is not a problem for us because we only have to verify that it's differentiable on the open interval. So the endpoints, whether it's differentiable at the endpoints, doesn't matter. So yes, this checks. Yes, we can use this one. Okay? So let's just practice determining whether you can use mean value theorem or not. You comfortable with that? All right, so on this one, it says find the value of c that satisfies the mean value theorem. So in other words, they've already checked for us. They don't say verify or ask you if you can. They're telling us to do that. Now, if you don't trust them, you can do the test yourself and determine whether it's differentiable and continuous. But they've told us to do it, so we can just go for it and use the theorem. So this is the theorem. So finding my slope of the secant, what are my point's going to be? Do I just get to pick any point I want? No, I have to use 1 and 3, right? This is my A, that's my B. So let's find the slope of the secant using this formula. So I sub a 3 in, and I get, so root 2 minus f of A would be 0 over B minus A, and that gives me root 2 over 2. So I have my slope of the secant. What am I supposed to do with that? Set it equal to the derivative, right? I've got to find this derivative right here, and I've got to set that equal to it. So root 2 over 2 equals, the derivative is 1/2 x minus 1 to the negative 1/2, and I have to chain it. What's the derivative of x minus 1? 1. So really turned into a non-entity, but I would, of course, have to do the power chain with that. All right, So then we would just solve that. Several techniques. Well, there's several ways to do it. I'll just show you the way that I did it. So this would be 1 over 2 root x minus 1. I cross multiplied, divided off the 2, squared both sides, and then solved. So I have x minus 1 equals a half, or x equals 3 halves. Okay. So I need to mention a couple of things about this. First of all, when I square both sides of an equation, I open myself up to extraneous solutions. Hopefully you remember that from pre-cal and algebra 2. It is possible to get an extraneous solution. So the safest thing to do would be to double check to make sure that it works. And you need to go back to the original, not to any of the iterations that we have. Go back to the original and see if my original derivative, if I sub in a 3 halves here, if it in fact equals root 2 over 2. And I will tell you in this case it does, but it would be worth checking. Okay, it'd be worth checking because I used a technique that will sometimes generate extraneous solution. Alright, well this one is fine. Is this one in the interval? Yes, so it becomes a C. In fact, if something happened and it wasn't in the interval, there's something wrong. Either I used the mean value theorem and I shouldn't have, it didn't qualify, or I've done something wrong in my solving, in my arithmetic or algebra or something. So just know that if the mean value theorem applies, it has to work at least one time. I have to get at least one C. I might get more. Okay? So are we okay with that?